Thank you, and thank you, Darren. It's great to be here. You can roll to the next slide. So in the first presentation, Jose focused on medical grade Tyvek from DuPont and the history there. Great job doing that. What I'm going to focus on is the coatings that go onto the Tyvek. That's our part of what we do, and then also some of the heat sealing processes that you might use in your facilities. First, to talk about the applications we're talking about, die-cut lids that go on rigid thermoform trays, pouches, and form-fill seal machines that you're probably all familiar with. So again, we're talking about the adhesive coatings that go onto substrates like medical-grade Tyvek and then are used as lid stock in those sterile barrier systems. So similar to Tyvek, we formulate our adhesive coatings to be compatible with many different sterilization modes. Some are listed on the screen. The common modes are gamma radiation, ethylene oxide gas, autoclave, and steam sterilization, and some of the other types of sterilization modes. We make our coatings so that they are compatible with those types of sterilization processes. Next slide. You'll see here a picture under magnification of what the coatings look like. So again, we're putting the coatings onto medical grade Tyvek. The picture on the left is a technology commonly referred to as water-based or air knife coating. In our industry space and dealing with Tyvek, really these are the two different types of coating technologies that exist. On the right is a hot melt. Exhale is our trademark name for it. It is a waterless system. Those blue dots are the dots of the adhesive that we tint blue in some cases, and then you can see the fibers of the Tyvek in between. So both technologies are available, or we make both types of adhesive coatings. So why are the coatings applied to the Tyvek? Well, they're a very important part of the sterile barrier system. They're there to allow for a peelable seal. So again, we put the coating on the Tyvek, and then when you create the seal with a film, in this case I'm holding a pouch, so that coating is there to give you that peelable seal that can be used in a clinical setting in the hospital, sterile field. It allows for the medical device to be presented in an aseptic manner by the clinician, the nurses, etc., just like that. So again, it's part of the sterile barrier system, and another important feature that they provide is that they give you visual assurance of the seal integrity. So difficult to see here, but you can see the white. That's the adhesive that's been released. We'll talk about that in a second, but clinicians, nurses, they look at that and they're making sure it's a complete integral seal, no gaps or voids that might indicate a breach of the sterile barrier. And then the last thing, regardless of which technology you're using, they both require heat to make them work. So in your sealing processes, heat, and I'm going to talk about that later, makes the adhesive activate and work. So we're formulation experts. We have PhDs, we have chemists in our facility. We're making our own adhesives. We're not buying the adhesives and then applying them. So what that looks like, this picture is kind of here to depict, we're buying the ingredients, pellets of polymer, which typically is EVA, ethylene vinyl acetate. That's kind of the backbone of our adhesives, most of them. We're using waxes, resins, and then a small percent of filler. So I'll get into more detail on the formulation, but it's good for our customers and people that are going to use our adhesives to understand the basics of the chemistry of how the adhesives are formulated. So again, we're buying all these ingredients, mixing them together. I'll talk about the processes in a minute, but that's the foundation of the adhesive. And then our formulators are working around theories of adhesion and cohesion, which I'll talk about more in a minute. So the two formulations the two technologies we talked about, hot melt and water-based, so Seal Science is our trademark name for our water-based, they are very similar in their formulas. They both use the same basic ingredients in that we're working with polymers, which are generally EVA, waxes, and resins. The primary difference with the water-based technology is that you've got water as a part of that system, and you've got some surfactant in there too to make it help wet it out. So I'm not going to go through every part of this slide, but it's just to give a general overview of the kind of things we're looking at when we do formulation of different adhesives. So in our portfolio, we've got something like 40 different custom formulas. So all we're saying with this is that, for example, when we're dealing with the different ingredients, there's different types of attributes that we're trying to make better, potentially. So adhesive strength. I'll talk about that, but if we want to reduce the adhesive strength, we might reduce the amount of wax in the formula, etc. If we want something that has really good performance at cold temperature, so if you've got a problem in your distribution environment where the packaging is put through really cold and shock, we can shift the formula around, increase the polymer content, and that can help have a more robust package with respect to cold shock performance. So not going to go through everything, but just to give you a general perspective of what we're dealing with when we make formulas. Okay, so this is a really important slide to understand if you're dealing with packaging and sealing in your processes. So it's really good to understand how the system works. So it's a cohesive peel system. That's how we design our adhesives. So you can see in this diagram, Tyvek on the top, adhesive in the middle, and the sealing film on the bottom. Or another way to look at it is if you have a lid stock in a tray, when you make that peel, the adhesive is designed to split. Okay, so some of the adhesive stays on the Tyvek lid, some stays on your tray or your package. That's how it's designed to work. So when you think about your sealing processes, doing things like troubleshooting and validation, just understand when you make this peel, some of the adhesive is still on the Tyvek, and some of it is this white transfer that you see on the film. It splits. So in that regard, we can control the peel strength by the cohesive strength of that adhesive formula. So we can control the amount of force needed to open a package by messing around or balancing out the formula with respect to cohesive strength of the formula. So this is going to be a video, and it does work, where you can actually see that process happening. And it's going to keep playing in a loop. So this is a side angle view of a sealed piece of Tyvek on a rigid PETG piece of film. You can see the adhesive splitting right there. Some of it's staying, some of it's going onto the Tyvek. It's just a nice visual representation. So a good question to ask later would be, what if you peel that up and the adhesive doesn't split? What if it completely comes up with the Tyvek? That'd be a nice question for later. So this is an animation of an air knife coating process. And again, that's what the adhesive looks like under magnification up in the upper right-hand corner. So you get the breathability through the cracks and crevices in the coating that's been laid down on the Tyvek. But the formulation aspects of this type of coating, as well as the coating process itself, all occurs at room temperature. So what's happening in this first applicator roller is that we're flood coating the Tyvek, complete flood coating, and then it's going to have an air knife that meters off the excess adhesive. And then that coated Tyvek is going to go into a series of ovens that will dry it and flash the water out of the formula. Next slide. So you'll see in this next slide, you can hold off on playing it just for a second if I pause it. But this is actual video of the coating process. The coating will typically look like it's got a milky white appearance to it. And again, this is all done at room temperature. So the roller down there is where the flood coating was happening. This spot right here is actually the air knife, and this is the coated Tyvek. So this air knife across the entire width of the web is blowing down and metering off the excess liquid or the excess adhesive before that web, and you'll see it go up into a series of rollers and then into a heated zone where the water is going to be flashed out of the coating, and that coating will be breathable for ETO sterilization. So that was the air knife coated process. This is the hot melt coating process. It's a little bit different, but again, the adhesives are designed to work in very similar fashions to the water-based. So this is a quick animation, then you'll see an actual video. You'll notice that the coater is much smaller footprint than the previous coater you saw for water-based. In this type of technology, we're taking those pellets of EVA resins and waxes and we're melting it down. So this is a heated process. We're melting those components down, we're pumping them through a series of pipes and into a bath here where we have a cylinder, so very similar to gravure printing, we have a cylinder that's got little micro pockets etched into it that it's picking up the adhesive, and then there's a doctor blade that's removing the excess adhesive, and those micro dots are applied to the Tyvek right at this interface. And again, we're talking about those micro dots of adhesive. So the next will be a video of the same process. You'll see the master rolls of Tyvek, And really the magic is all going to happen at the interface. And you'll see a silver cylinder where we're going to be applying the molten adhesive. So again, the adhesive is going to be hot. It's going to be controlled at about 300 degrees Fahrenheit. And it's going to be applied right at that interface. But this is the cylinder that's rotating and applying the adhesive right there. After it's applied, then it hits a chill roll to cool it down. But prior to that, it's at high temperature. Yeah. So I get a lot of questions, well, which adhesive technology should I use? And really the answer is both have been around for almost the inception, or since the inception of Tyvek. So they're both heavily used for sterile barrier packaging, and in most applications, either one will work. There are some nuances that are a little bit different, and I'm going to walk through those slight nuances. But if we compare exhale or hot melt to a water-based coating, one thing that is significantly different is the adhesive anchorage into the Tyvek. So we just saw that video, and if you think about the dots of adhesive that are a part of hot melt, they're molten, they're at high temperature. So when they hit the Tyvek, they're hit with an impression cylinder and they're driven into the Tyvek, and because they're molten, they grab the Tyvek fibers and anchor very well. With water-based, you saw it's a flood coating on the surface, and then it goes into an oven to dry it. It's kind of sitting on the surface of the Tyvek. Has pretty good anchorage, but if you've got like a device that's going to rub against the lid stock, you can get situations where you've got some particulate generation. So you have to be careful about that. Whereas with hot melt, because of the way it's made, with that molten adhesive, it really anchors well to the Tyvek and is less likely to rub off and particulate. A good demonstration of this is just to use some common Scotch tape. If you take tape and apply it on the surface of the coated Tyvek and pull it up, with hot melt, it's not going to come up. You're going to get no adhesive pulling up. With the water-based, you're going to see some pieces of adhesive that come up. So depending on the application, we will promote hot melt or we'll promote water-based. If it's a highly sensitive device or a pharmaceutical that's very sensitive to particulate, we would almost always steer our customers towards the hot melt. A couple other things we're going to talk about. Endotoxins. So I'm not a microbiologist, but endotoxins are essentially, Jose talked a lot about microorganisms and things that can cause reactions in patients and infection. Endotoxins are basically dead microorganisms, but dead microorganisms can still cause reaction in patients. They can still cause infection. So it's important, and we get many customers now that are starting to ask us, can you report back to us what your endotoxin counts are in your adhesives? A very significant difference is that the hot melt system doesn't have any water in it. Water-based obviously does have water in it. Water inherently has a lot of endotoxin potential in it. So even after sterilization, you've got the potential for reactions in patients. Peel strength is the next characteristic we're going to talk about. So we have two seal curves here. This would be outputs from our customers' sealing processes. So this would be your sealing temperature on the x-axis, and this is the output of the seal strength in pounds per inch. One slight difference between the two technologies: with hot melt, you're generally going to have a flatter seal curve, meaning at your low temperatures versus your high temperatures, your peel strength should be somewhat stable. So from a statistical standpoint, there can be some benefits there. With water-based, you generally have an upward trend in the seal curve. So at lower temperatures, your seal strength might be a little bit lower, and as you go up in temperature, you can cause your seal strength to go up. So for our customers, it can be a user preference. Some engineers that buy from us, they prefer to have a nice flat seal curve. Some like to be able to have the ability to strengthen the adhesive during their process and manipulate it that way. So the seal indication, the adhesive transfer, that's another characteristic that it's a little bit different. So with the hot melt, think about the dots that we're applying. So in your sealing processes, you have to get those dots to activate, flow, and merge together to get a continuous seal. With the water-based, you've got a flood coating, so you're not having to get dots to merge together to get a good adhesive transfer. Again, it's back to user preference. Some people really like to have the hot melt, because it can be a seal indicator. When the dots are not merged, it means there's something wrong with your sealing process. The water-based can be much more forgiving, and in a sealer that maybe has some issues, you can get a good cosmetic seal more easily with the water-based, but it's a nuance that's slightly different between the two. One other characteristic, seal gasket wear. So if you think about a sealing process, you've got rubber gaskets that are part of that process. One difference is that with the hot melt, you usually need less pressure in your process to get a good seal, and I'm going to talk about that more later. With water-based, they typically work better at higher pressure. So you'll get a little bit more wear with your seal gaskets when you're using a water-based system, so you just have to think about that during your PMs, your preventative maintenance procedures. 3 more characteristics. Porosity. Jose alluded to that a little bit. Think about hot melt and those dots, and in between the dots you've got open area. So from a porosity standpoint, hot melt is almost always going to be more porous than a water-based system that's going to be flood coated. So if you look at Gurley Hill seconds, that's the amount of time to get through the substrate. 30 seconds is, lower is better. It means it's more breathable. For ETO sterilization cycles, you're going to get the gas in, the gas back out, get your residuals out faster with a hot melt process versus a water-based. And then a yellowing factor, be careful if you're using a water-based adhesive coating. Some of them have a tendency to yellow over time and with exposure to UV. It's a cosmetic problem, it's not a functional problem, it's not a patient safety problem, but just beware of that. That picture kind of shows it, but it's a slight yellowing that can occur. And then the last one before the translation, the seal creep is a scenario where strength of the adhesive at higher temperature. So during EO sterilization, it's elevated temperature. During transportation in a warm climate, it's elevated temperature. Adhesives, almost all of them are going to get a little bit weaker when they're warmer. So some of the water-based coatings in our portfolio have really, really good strength at high temperatures during EO, so they're very creep resistant, meaning creep to open. All right, so that was a nice discussion on heat sealing formulation, heat seal coating processes, how they work. So we're going to focus now on the heat sealing process itself, which is really important. It's going to be kind of a 101 generic look at in our customers or your sealing processes, what are the variables and things to really pay attention to. So the first thing you need to understand about making a good heat seal is that temperature is the most important factor. So if you're doing a design of experiment during your getting ready for validation, temperature is really what you want to focus in on. So just visualize in your mind, it's a pretty basic process where you're taking a heated bar, you're marrying 2 materials together with heat, and then you're using some dwell and pressure as well, but you're just marrying the 2 together to get a heat seal. Temperature is the most important factor to pay attention to in your experiments. And then dwell time is the second most important factor after temperature. The temperature in your sealing process and the dwell time work together. Visualize it that way. You can use higher temperature and shorter dwell time to optimize, or you can have lower temperature and longer dwell time to make the same thing happen. You want to balance it out, and that's how you should look at it. So I was going to go over this, but I think you probably covered it. This is a good way to visualize in your sealing process. You need to have enough time to get through the Tyvek, get the adhesive to activate, and then get enough heat into the system to get the adhesive to activate and also bond to your film. So if you think about your sealing processes, depending on the thickness of this film that you're using, thicker films might require a longer dwell time to make this whole thing work. So it's just a good visual representation of any sealing process that's good to understand. And then the final thing you need to consider is pressure. So it's all about temperature, dwell, and pressure. Pressure is the least important, but it can also hurt you, so be very careful with pressure. Most of the customers that I deal with that are having a problem, they use pressure too much. They put too much pressure into the process, and that's a problem. So just be very careful. Pressure is something, it's really just there to get the 2 materials to mate together and allow the heat and the dwell time to work together to make a good seal. So just be careful with pressure. Too much pressure is a problem. If you think about impacting the materials with too much pressure, you can get that adhesive to go up into the fibers of the Tyvek. You can get it to squeegee out from the seal, and that means you have less adhesive at the interface, which makes potentially a less robust seal altogether. So now let's talk about how to optimize your sealing process. So you're working on your equipment, you've got two materials you're now asked to qualify. It's a process to go through. This is one example where your sealing process is not optimized, and it's usually pretty obvious. So this is a seal curve again, where you've got an output of seal strength. This is your sealing temperature. In this type of scenario, we've got adhesive transfer that's not continuous. It's splotchy, it's not a complete looking seal, so you know you don't have enough temperature or dwell time as a part of your process, and it's obvious visually, and it's obvious because your peel strength values are low. So this is another example where you're not optimized, but it's not quite as obvious. So especially if you're using a water-based coating, you can be not optimized, meaning you don't have enough temperature or dwell time, but cosmetically the seal looks great. However, when you start measuring your peel strength values, they're going to be a little bit low, they're not going to be very consistent, you might have a lot of variation, so just be careful about that type of scenario. This is also a very common occurrence that I see with our customers when I'm troubleshooting, and that is to go to the other end of the spectrum and overseal it. So the thought typically is, hey, I want the strongest seal, so what I'm going to do, I'm going to use the most temperature and the most pressure to try to make a really strong seal, but that's not necessarily a good thing to do. So in this slide, we're showing that, hey, we're way down here at high temperature, 280, 290 degrees Fahrenheit, and that can cause problems with what you see in the picture. You can get the Tyvek to start tearing. You might be transparentizing the Tyvek, making it clear, so you're basically melting the fibers, and that can just contribute to that picture, what we're seeing there. And then your adhesive transfer at that upper end can also look kind of differential and spotty. So be very careful to go too high in your sealing process, and we call that oversealing. And this is where you really want to be at the end of the day. Once you've gone through your experimentation and your validation, you want a window to work within. And we talk a lot about ISO 11607 in our industry, but ISO 11607 tells you should have a window to work within in your sealing process where you've got low temperature, low pressure, low dwell time, and also a defined window at the upper limits where you've got a consistent output of peel strength, you've got a good cosmetic looking seal, and that is where you want to have your validation defined at. So we're going to transition to a new grade of Tyvek, and it's going to be covered by the DuPont folks, but you can go to the next slide. 40L, and at Oliver, we've coated this with a water-based coating, so our nomenclature is ST-40L Tyvek. So it's coated with our Seal Science adhesive, and really has nice, consistent, and smooth peels when we peel it off of various films. Works very well in a form-fill seal application. We've done a lot of testing in that regard, and it works very well. Also in pouch configuration, works well as also. So as I said, very good sealing and peeling characteristics. That's a nice seal curve we've generated with a flexible forming web, but we're getting values between 110C all the way up to 127, 132C, and peel strength output well over a pound, so that's impressive to us. And then the adhesive transfer properties combined with our coating also look very good. That's a picture of a peeled open form-fill seal package.